This is a video lesson for 5.1, and this is part 1 of 5.1. We will be exploring stretching and reflecting quadratic relations. Our learning goal is basically to take our typical standard parabola of y is equal to x squared and then transform it in some way, modify this equation and see what happens to the graph. So for example, if I have y is equal to x squared and it looks like this, what would happen if I get y is equal to ax squared, where a is something different than 1. This is 1x squared. What if I make it 2x squared, or 3x squared, or 0.5x squared? Or what if I make it negative x squared, or negative 2.5x squared? So how does changing that a value affect the y is equal to x squared graph? And so what we're going to do is we're going to explore that before we make our conclusions. We're going to start off by finding values for y is equal to x squared, 3x squared, 6x squared, 0.3x squared, and 0.6x squared. And then we're going to graph those and see what conclusions we can come up with. So I'm going to start off by doing a few of these examples in this table of values with you, just so that we can go over how to do that properly. And then I'll go through them quickly because we should have some expectation that we know how to fill in a table of values at this point. You've done it several times in previous units. So y is equal to x squared is the most straightforward one. So let's say, for example, you want to find the y value when x is equal to negative 3. What you would do is you would do y is equal to negative 3 squared, which would be 9. In this case, the value that's in front of the x, since there's none there, it's an implied 1. So you could do the same process for when x is equal to negative 2, y is equal to negative 2 squared, which is 4. And we keep doing that throughout. So 1, 0, 1, 2, and 9. Let's look at y is equal to 3x squared. So our a value is no longer 1, it's now larger than 1. It's 3. And you can find your y values for the different x values here. We decided to choose x values that were nice and symmetrical and easy to work with, negative 3, negative 2, negative 1, 0, and then we chose equivalent ones but on the positive side. So let's try when we have an x value of negative 3, we have y is equal to 3 times negative 3 squared. And that gives you 3 times negative 3 squared, which is 9 here, which is 27. So what you may have noticed is that this graph of y is equal to 3x squared is simply 3 times x squared, right? So we had 9 over here. Now that we have 3x squared, it's 3 times 9. So 4 over here, so 3x squared would be 12. 4 times 3. 1 times 3 is 3. 0 times 3 is still 0. 3 again. Oops, and over here I made a mistake. This should not be 2, this should be 4. And that would make this 12, and then 27 again, right here. So we can do the same thing with the remaining ones. So here we have a is equal to 6. And what you may have guessed is you could simply take your x from the y is equal to x squared, or your y from the y is equal to x squared, and multiply it by 6. So we get that 54, 24, 6, 0, 6, 24, and 54. So these two are for the cases where a is larger than 1. And I also want you to get that right now we're exploring the case when a is positive. Notice we don't have any negative a's right now. We don't have negative x squared or negative 2x squared. Right now we're dealing just with positive. We'll take a look at how negatives affect us in another video. Right now we're dealing with a's that are positive, and we have a set where a is larger than 1. We're also going to have a set where a is smaller than 1. Here we have 0.3 as our a, and 0.6 as our a. So these two would be the case where a is less than 1. Still positive, but less than 1. But it's the same idea. You can multiply the y value of y is equal to x squared by the a that's in front of it to get your new y value. So we would have something like this. We'd have 2.7 over here, 1.2, 0.3, 0, 0.3 again, 1.2, and 2.7. And the same idea for the 0.6 here. We have 5.4. We have 2.4, 0.6, 0, 0.6, 2.4, and 5.4. And so the idea is that we're going to plot the y is equal to x squared graph first, and then plot the other ones on the same grid to compare how they look in comparison to the x squared. So how does 3x squared look compared to x squared? How does 6x squared look like compared to x squared? Likewise, how does 0.3x squared look like compared to x squared? And how does 0.6x squared look like compared to x squared? So we can put those all in the same grid. Once you get the sense of what the positive a does to the y is equal to x squared graph, you'll be able to look at a graph and come up with a reasonable conclusion as to which graph could be associated with what type of equation. Notice that on this grid here I didn't include any negative values, or very few, only because we don't have any negative y values, I should say, negative y values. They're all positive since we have that x squared going on here. I won't be able to plot all the points here. I'll only be able to plot a few that will fit on the graph. I could, if I wanted to, choose an appropriate scale to do that, but I'm just going to go up by one. It's nice and simple, and I can just connect a few dots to make the parabola. Now, again, mine won't look that great because I'm using the mouse, but you'll do a nicer job, and you'll compare to mine and say, wow, I'm way better than Mr. Yafate at making these parabolas now. So we'll start off just by going up with units of 1. So 1, 2, 3, 4, 5, 6, 7. And then same thing with the negative end, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'll start by plotting y is equal to x squared. When we have negative 3, we have negative, when we have negative 3, we have 9. So 1, 2, 3. Then we go all the way up here to 9. When we have negative 2, we have 4. Negative 2 here, 4 here. When we have negative 1, we have 1. When we have 0, we have 0. When we have 1, we have 1. 2, we have 4. And then 3, we have 9. And then we can connect those dots as neat as you can, as smooth as you can. And we can label this as y is equal to x squared. And I'm going to choose a different color for my y is equal to 3x squared. I'll just choose green. So same idea, I won't be able to put 27, but I can put, when you have negative 1, you have 3, so negative 1, 3. When you have 0, you have 0. When you have 1, you have 3. And we can't really fit the 12 there, but we could try. When you have negative 2, you have 12. So we have 11 over here. 12 would be about up here. You could extend that grid. When you have 2, you have 12 would be about up here, just so I could show you roughly what the shape looks like. So like this. And then you could just kind of extend it, aim it towards that dot there. Same thing here. And aim it towards that dot over there. Again, please make sure you're making nice smooth curves, unlike this one here. It's difficult to do with the mouse. And so this is equal to y. This is y is equal to 3x squared. And then we'll put our y is equal to 6x squared in there as well. Let's choose a different color for that so we don't get confused, it's always good to label your graphs all the time. Otherwise, mistakes will happen. So we can do the -1, 6, -1, and 6. We can do the 0, 0, and we can do the 1, 6. Like that. We can connect those dots nicely over here. And do the same thing on this side. And so let's do an analysis quickly. Well, let's just label that actually. Y is equal to 6x squared. So notice we just plotted the ones that are a being larger than 1. This is our original y is equal to x squared, where a is equal to 1. And notice that as we increase the value of a, so when I go from y is equal to x squared to y is equal to 3x squared to y is equal to 6x squared, we are actually stretching the parabola. The parabola is stretched from the vertex up. Like take an elastic, when you stretch the elastic, it becomes skinnier. So it becomes narrower. You'll notice that 6x squared is narrower than 3x squared. And that one's narrower than just x squared. So the higher that a value, the more narrow your parabola becomes. And when you think about it, it makes sense because the parabola is rising faster with a higher a value. You're multiplying for every unit you go up. So for example, if I go up 1 unit for y is equal to x squared, y is just 1. If I go up 1 unit for y is equal to 3x squared, y is 3. So it's going up 3 times faster. If I go up 1 unit for y is equal to 6x squared, we get y is equal to 6. So that's rising 3 times faster. So when you have a is larger than 1, what that means is you are stretching the parabola and you're making it more narrow. You're stretching it from the vertex over here and making it more narrow. Notice that you're able to go from the y is equal to x squared graph to these other graphs by doing simple transformations, by multiplying your y value from your x squared to get your new y value from your other modifications, your 3x squared and your 6x squared as well. So that's what happens when a is larger than 1. You stretch the parabola and make it narrower. What we're going to examine in the next video is what would happen if a was less than 1. So in other words, we're going to draw the remaining parabolas over here with 0.3 and 0.6 and take a look at what happens in that case there. Will the parabola be stretched, or will it be compressed? Will it become wider? So think about that, make some predictions, try drawing them out yourselves, and then compare in my video to see if you came up with the same conclusions that we would for that we did in the video.